All right, let's get started with this SI sheet. First starting off, we got to figure out which of these molecules here would react with just water, without sulfuric acid and without a base, and give us a carboxylic acid. So let's look at all of our options. We have two anhydrides, we have two acid chlorides, two esters, and two amines. So we have all four of the carboxylic acid derivatives. And if you notice the difference between the same set of carboxylic acids derivatives is that one of them has a longer carbon chain than the other. So normally, I don't know if Dr. Mullins wants you to know this, but you'll eventually learn it in biochem. If you don't need to know it here, you will eventually need to know it in biochem, is that the longer the carbon chain, the less soluble it is in water. And the reason for that, you might not need to know for this class or not, is when we talk about water stability, we look at water's ability to surround a molecule. So if you have a longer carbon chain, then it's going to be harder for water molecules to surround the molecule because, like, let's say, for example, for this ester, it takes 6 water molecules to surround that ester. For the smaller ester, maybe because it's smaller, it's only going to take these 4 as opposed to 6. So that's the reason why a longer carbon chain is less soluble in water, because it's harder for the water to surround that carbon chain. So given that, the smaller carbon chains are always going to be more soluble in water. But we're looking here at what's going to react with water. So acid chlorides are the most reactive. So acid chlorides are going to react with water, and the small one is going to react better with water than the long one because it'd be easier for water to surround this acid chloride chain. On the carboxylic acid derivatives, what's the next most reactive? The next most reactive is an anhydride. And then for the same reasoning that the smaller acid chloride would react better than the longer acid chloride, the smaller anhydride is going to react better with water than the larger anhydride. Then once you leave, so an acid chloride and an anhydride are on the top of the carboxylic acid derivative ladder. Once you get past, or when you're going down and once you get past the anhydride, then the reactivity really falls off. So although this ester is small, an ester isn't going to react with water to create a carboxylic acid. It's not reactive enough. And then an amide is even less reactive than an ester, so an amide isn't going to react either. So just these two molecules are going to react with water to create the carboxylic acid. All right, next one, we have to show the, oopsies, what's going on here? Oops, fix this really quick. Um, there we go. Okay, we have to show the mechanism for one of the molecules we chose. I'll do the acid chloride just because it's easier to write out. But either way, it's going to follow uh, exact same similar mechanism. So an acid chloride conversion to a carboxylic acid. So although water is a weak nucleophile, in the aldehyde and ketone chapter, we learned that water wouldn't be able to do this if this was an aldehyde or ketone, and that's correct. Because aldehydes and ketones aren't reactive enough to react with a weak nucleophile like water. But because an acid chloride has 2 electronegative atoms, let me draw on the dipoles, 2 electronegative atoms pulling the bond away from this carbonyl carbon, that makes this carbonyl carbon have a big partial positive charge, which allows a weak nucleophile to actually come in and attack it. So that's going to happen. The first step, water is going to attack the acid chloride. And then let's draw the result of that. We're going to have a Zwitterion. And chlorine's a good leaving group. And if you look in our final product, we don't have chlorine in the molecule. So what's a good leaving group going to do? It's going to leave. And this oxygen trying to solve its or account for its negative charge is going to do resonance to help kick out that chlorine. So what we have here now is we have our carbonyl. And we just have to deprotonate in order to get to the product. So this would get us to the product. So that's the mechanism. Normally, you're gonna see all carboxylic acid derivatives be converted to carboxylic acids, not under the presence of water. Usually, it's gonna be acidic or basic conditions. But just wanted to show that because that is in the book that small acid chlorides can react with water to create carboxylic acids. So now we're going to see what's going to be a more common way to create carboxylic acids under acidic or basic conditions. So here, first, identify if it's acidic or basic conditions. Because we have a metal, we're going to have an ionic bond, giving this hydroxide group a negative charge and making it strong. So strong nucleophiles, they're going to attack electrophiles. Our electrophile here is the carbonyl carbon. Because it's strong, it can just attack right away. So let me draw the other one since I'll explain. It doesn't matter which one you attack, but I'm gonna attack the left one because this carbon appears to be on the left. So I'm gonna make sure that carbon is on the left here. Draw the result of this. We get a negative charge on the oxygen. And then what's separating us from where we're on the product? This oxygen needs to create a double bond with the carbon. And then we need to kick off this acetyl or acetal group. So, or I should say acetate group, oopsies. So this gets us to the product. And this is a decent leaving group because when you have a negative charge, this can do resonance, stabilize the negative charge. Not the best leaving group, but decent. Not as good as chloride, but not too bad. So that's basic. Basic conditions are always quicker than acidic conditions. So let's move on to the next one. This will take a little bit longer because it's acidic conditions. We know it's acidic conditions because we have a positive charge, and because we have hydronium, we have a strong acid. So what's always first in acidic conditions, you're always going to protonate the carbonyl oxygen first. And we have to protonate because eventually we want water to come in and attack. But water is a weak nucleophile. And although because it's an anhydride, water would likely attack, we're in acidic conditions. And if we had water attack, that create a negative charge. Since we're in acidic conditions, we shouldn't create a negative charge. So we're just going to show the protonation of water first, since we're in acidic conditions. And then now we have a protonated carbonyl oxygen. So now we can take our water, a weak nucleophile, and attack a stronger electrophile because there's a positive charge. And then draw the result of this. Now we have an alcohol, and then we have a hydronium group. So how do we solve for the positive charge? Deprotonation. Take water, take a hydrogen in order to get rid of that positive charge. So now we're going to have two alcohols here. If you look in the product, we don't want this acetate group here anymore. So we're going to want to have it leave, but we can't have it leave right away because if we have it leave, then that's going to create a negative charge. We're in acidic conditions, so negative charges shouldn't be made. So to avoid a negative charge being formed while still allowing this to leave is we're going to protonate the oxygen. And I'm gonna protonate this oxygen actually, and I'll show why. So now that this oxygen is protonated, we're still gonna have this group leave. So we need to have one of these oxygens form a double bond. And we know that because in the final product, we want a carbonyl. And then instead of having the electrons go to the oxygen, I'm going to have the electrons then go to this bond right here to form a double bond, and then push the electrons onto the that oxygen to get rid of the positive charge. And then this avoids a negative charge being formed. I don't know if Dr. Mullins will be okay with you having protonating this oxygen specifically. Talk to him about that. But I know this would be correct to protonate the top one. So let's show the result of that. We kicked off our acetate group, so now we have carbonyl that's protonated, and what's separating us from where we are in the product is just deprotonation. So that's the mechanism under acidic conditions. The longer one. Acidic conditions are always longer. Normally, acidic conditions form the thermodynamic product, where the basic conditions form the kinetic product, but I don't know how much of that concept we're going to show for this test. All right, next one, predict the products if alcohols or hydroxide groups are used instead of water. So let's just draw in what would the result be if it was water instead of the hydroxide and what do you call it? Hydroxide or alcohol groups. So we know from the previous page that if we just use water, we just make carboxylic acids. Because we have water, water is going to lose one of the hydrogens, and the other bond it gains is to the carbonyl. And that's going to be the same thing. Or it's what I just said is going to be somewhat the same, even if we use alcohols or hydroxides, in that this ethanol, it's the oxygen is going to lose the hydrogen while keeping one of its bonds and then gaining a new bond to the carbonyl carbon. So this ethanol, it's going to lose the hydrogen, and then the new bond it's going to gain is to the carbonyl carbon while still having the ethanol or the ethyl group attached. And then this one, it doesn't have a hydrogen to lose because it's already lost it. So then the one bond it's going to gain is to the carbonyl carbon. Like that. So let me just throw in water again. The concept remains the same. Whatever alcohol group is using the reagent is going to lose one hydrogen, gain a new bond to the carbonyl, and gain a new bond to the carbonyl. So if we replace it with an ethanol, it's going to lose the hydrogen, and then the bond it's going to gain is to the carbonyl. That might be a quick way to remember it. What functional group do we make here? You'll see that these are esters. So now we have to predict what reagents would create these following transformations and try to use the previous answers as a guide. This one might be the easiest to do because if you look, we made an ester. And we just made esters using this method. So to make an ester, we need to use an alcohol or hydroxide group. And we have 3 carbons here. So our alcohol or hydroxide group should have 3 carbons because that is the alcohol that is going to add to create the ester. And then I chose an alcohol, so we'll do acidic conditions. If you want to do basic conditions, then what you should do is use a metal attached to the oxygen instead of a hydrogen. But I'm going to do acidic conditions for this one. And then sulfuric acid for acidic conditions. Okay, next one. We're making an anhydride. So this is the group we need to attach because the left side is going to stay the same. What changes is that we get rid of the chlorine and replace it with a acetate group to make an anhydride. This blue is the acetate group. So we need to add this on. So in the reagents, we should have this. And then to make anhydrides, we're gonna use a metal. We're not going to use, in this case, acetic acid. We're gonna use a metal. And then let's just grab a solvent, water. THF will be fine too. So, yep. Next one, we're making an amide. So once again, we're gonna keep the left side the same. And then we need to add on the nitrogen part to get rid of the chlorine. So this is what's going to go over the arrow then. NH3. Because when this adds, it's going to eventually lose 1 hydrogen. And the way it gets deprotonated is we do 2 equivalents of that because we use 1 equivalence to attack the carbonyl, and then the second equivalent is going to deprotonate to turn this into 2. So that's why we use 2 equivalents of that. So that was the SI sheet. Let me know if you have any questions.